So this is a to-do list for the rest of the course. So we have 5 lectures and 5 topics. We'll stop as soon as we cover all of these. Fine? Or you want more? So should we stop as soon as we cover these, or should I continue teaching till the very last class?
Sir, you were about to teach the digital in the next course, right? So we
You
can,
want
you
me
can.
to? Yeah.
So I guess it's your format method is good enough.
So I'll stop. So that digital, I've seen that the syllabus has. So the official, I have to follow the official syllabus to some degree, or I have to be guided by the official syllabus. And in the official syllabus, what they have done is they have merged 2 courses: digital communication and information theory. So
Okay.
that digital communication is quite different from what used to be digital communication till last year.
Okay.
Anyway, I'll so yes.
Sir, but the main issue is that you were supposed to take Viva for 7 days. So
Yes.
want it troublesome for you
See,
if
yeah, I'll finish. Okay, I'll finish these topics and be done with it. And as soon
yes,
as we finish these topics, we'll start with the Viva. Maybe I'll make the Viva lighter for myself.
sir, the Viva would start from 24th or 23rd
I'll
because
give you a schedule when we finish the classes.
okay, sir.
So if we finish these topics next Tuesday, I can start the Viva next Thursday or next Friday. Okay.
Okay, sir.
So for you, it's just a 15-minute affair, 15 to 20-minute affair. I am on the receiving end over there. So yeah.
Yes, sir.
K goes from mine. We had said this, that this is 0 in the mean squared sense. Now, in order to prove this, let's expand this. So the expansion would be, so like we used to do in class 6th. Expectation of this square, right? What would be the expectation of this thing whole squared? Guesses? Okay, I'll write it down. Summation k minus infinity to infinity. Summation L goes from minus infinity to infinity. X KTS X LTS sync 2W T minus KTS sync 2W T minus LTS. Fine. Minus twice expectation of summation k goes from minus infinity to infinity x t x kts sync 2w t minus this is fine.
Sir,
Yeah.
uh, the sign part will not
Sync.
be creating, right? Sync part will not be creating problem, right, in this expectation.
See, sync is a constant or sync is a deterministic function. So the expectation of sync is sync.
Okay, it will just come out.
Yes. And so let's evaluate these terms one by one. Expectation of equals, right? This is right.
Yeah.
And let's first look at the third term. So summation and expectation are both linear operations and their orders can be interchanged. So if I call this term as let me call this term as 3 or let me call this term as 2. So 2 I can write as summation k goes from minus infinity to infinity, L goes from minus infinity to infinity, expectation of x kts x lts sync 2w t minus kts sync 2w. Fine. This is okay.
Yes, sir.
Good. So this equals summation k goes from minus infinity to infinity, L goes from minus infinity to infinity, Rxx k minus L ts sync 2w t minus kts sync 2w t minus lts. Again, let k minus L equal m. This becomes summation k goes from minus infinity to infinity, summation m goes from minus infinity to infinity, Rxx m ts sync t minus kts sync 2w K minus M. TS, fine. This is okay. This is okay.
Yes, sir.
Okay, great. So since this is okay, we now try out something even bolder, and K goes from minus infinity to infinity. Sinc to W T minus KTS summation M goes from minus infinity to infinity. RXX MTS sinc K T minus K minus M TS. Fine.
Yes.
Okay, great. So but that RXX tau is band limited to W, right?
Yes, sir.
Since RXX tau is band limited to W, RXX tau equals summation K goes from minus infinity to infinity RXX KTS sinc, which means that we can basically reconstruct RXX tau, since RXX tau is deterministic, and since RXX tau is deterministic and band limited, we can reconstruct it from its samples.
So can you repeat this part?
Yes. So RXX tau is band limited by definition.
Yes, sir.
RXX tau, this is the key part, is a deterministic band limited signal in tau, right?
Yes, sir.
Which means, sorry, which not which means, which means we can reconstruct RXX tau from its samples, right? Which means fun. right? Makes sense?
Sir,
Sorry.
uh, yes, but sir, wasn't it RxS M tau? Why it
So
became K tau?
see, that's that mk, that is, oh sorry, not this. Yeah, this should be t minus k tau. I wrote the above expression. So this should be rxx k tau simply.
Okay, okay.
Yeah.
Now. Yeah.
Yeah. So sorry about that. That I just wrote it and I just copied that part from above, which means one, right? Now, based on
Now,
this, we can reduce this expression. This expression, therefore, reduces to, you just substitute and yes, t minus kts. One, fine. And so, therefore, 2 equals summation k goes from minus infinity to infinity r xx, or rather sync. Fine.
yes, sir.
Okay, great. So since we get this, so this again by the same logic, right?
Sir, we are taking that k equals to 0 part, right?
K equal to minus infinity to infinity. We are summing this, and again it. Oh, okay. So you have to apply the result of problem 2.42 of ProCase. Just a second. So if I go to problem 2.42 of ProCase, yeah. So I had that as a side note. Let me open ProCase and 2.42. So problem 2.42 says that yes, actually, if you try to solve problem 2.42 of ProCase, you will get this. Okay, I'm not solving that right now. I'll take that as a granted result. This and similarly, you can show that this 3 within 3 or within the third term, this part within the, yeah, within the third term. Okay, yeah, pen has started working. Yeah. this. Fine. So again, what we get is that the LHS becomes Rxx 0 plus Rxx 0 minus 2 Rxx 0 equal to 0. Fine, I'll just state 2.42 or 2.42 of PoC as a result that actually this is the result. X0 equals summation k goes from minus infinity to infinity x ts actually this. Yeah, this thing is obvious actually. See, this will be 0 only for this will be x, this will equal x0 only at k equals 0, otherwise it will be 0. So this is true. You follow this?
Yes, sir.
Excellent. So since you follow this,
So can you go up a bit?
yeah,
Here, but here we don't have that RXX of KTS form.
you have this form.
So we are taking it T equals to KTS.
Yes. Okay, just let me again, I'll just open the book. Maybe I'm missing something while
Right?
trying to prove this.
RXX of T.
Just a
Then
second. I'll just cross check
yes,
because I might be missing something. So this and so yes, see, this is right actually. Yeah, this is right because this form you can replace this t minus kts for any t and this will become or you can subtract any constant from everywhere and it'll give you the same samples. You get the point?
okay,
Okay, because see, had this been rxx kts, then it would have been the reconstruction of those samples. But here what I'm doing is I'm subtracting this t on either side, so you can as well assume this t to be 0.
okay. That is
And
a
thankfully the autocorrelation function is even.
yes.
So that's why we skipped these steps.
Okay.
Fine.
Yes, sir.
Excellent. So this is how we can, or this proves that we can sample random processes and get away with it in a mean squared sense. So we can sample random processes and get away with them, or we can sample band limited random processes in a mean squared sense. Fine. So this completes the discussion on sampling. That can now convert an analog signal to a discrete time.
Hello, sir.
Yes,
Yes, sir. Why are we concerned that the mean squared dif- difference of the sampling is actually zero? So that it
we
is
say that
reversible.
we are concerned because this means that in a mean squared sense you can reconstruct it truly. There is no error. There is no reconstruction error in the mean squared sense.
So why are we choosing mean squared sense? Like, what's it? Like, why mean squared sense?
Okay, so uh, how do I say this? Let me. Okay, you guys have. Okay, you guys haven't done estimation, right?
Sir, some of us have done.
Some of us, not all of you.
Yes, sir.
Right. So I uh, don't want, I want to tell everyone, not just 5 people or 6 people. So
Hello.
yeah,
Sir,
Adit.
in DSP, we are currently doing some form of estimation.
Sorry,
In DSP, we are currently doing some of form of estimation.
the DSP, you don't have randomness.
Yes, that's also issue.
Yeah. So, Adit,
Sir, actually, sir, my internet connection is patchy today. Can you repeat the answer to my query?
what was your query? Why do you want, why are we talking about mean squared
So,
sense?
yes, sir.
Okay, so yeah, I'm thinking about that answer because it's hard to answer that without introducing notions from estimation theory.
Okay,
Uh,
sir.
the simplest way of saying it would be that you want to minimize the error. Okay. Okay. Once
Okay,
we
for
talk
the
about quantization, maybe I'll become slightly more clear.
okay, sir.
So maybe in the next 15 minutes, you'll get the answer to your question automatically. And in any way, you can see that mean squared error is the error power that you might notice directly.
Yes, sir.
So we are minimizing the power in the power of the error. For now, let that work. And I will come to it when we discuss maybe in 15 minutes when I discuss quantization, you'll understand mean square error slightly better. So we
Okay,
have
sir.
covered sampling. Now the second topic, quantization. So after sampling, we have a discrete time continuous amplitude signals, but digital signals can only, or digital systems can only deal with signals that have discrete amplitudes, right? Actually, binary amplitudes, I'm yet to provide a proper proof of my words, but uh, this we all agree that digital systems can only deal with systems that have discrete amplitudes,
Yes, sir.
because dealing with a continuous amplitude would require an infinite precision, and infinite precision would require an infinite length shift register, which is not possible. So we want to discretize.
Sir,
Yes.
sir, just a slight detour. Sir, in
Yeah.
that PLL, the
Slide.
phase
All
lock
the
loop.
slide detour.
Uh,
Okay. Yeah. Ask me something from uh, my previous life.
Sir, sir, just I'm asking that in that PLL part, we had that phase to be continuous as well, and we were trying to bring the phase to zero.
Phase
Was it?
error. Phase
Ye-
error.
yes, sir, phase error. In
Yes.
that case, also the phase error was continuous.
So
It
is
wasn't.
PLL a digital circuit?
So what?
Is PLL, is the phase lock loop a digital circuit?
No, sir.
Does that answer your question?
Okay, 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 okay. Now, got it.
Yeah. We want to discretize the continuous amplitude samples xn. Fine. So you had xt. You sampled it. You got xn. Now, so basically, quantization is a mapping from the real line to a finite set, say B. So if I define this Q x, this is basically B, where B fine. So B is a set of representative reconstruction levels that can be, or B set of numbers called reconstruction levels that used to represent xn. Fine. what we are basically doing in quantization is that, say, then if xn lies in the interval ai, then q of xn equals pi. Fine. As an example of quantization, say I tell you that there are so as an example of quantization, because that's important. Say tell you that want 3.141592653997 grams of gold, because this precise quantity can only be for gold or platinum or something like that. I'm not that rich actually, but yeah. Say I want this. So would you go tell a jeweler that you want this much gold? In general, if say, how expensive is gold anyway? Any idea?
Sir, 45,000 for 10 grams.
45,000 for 10 grams. Okay. So 45,000. So let's approximate it to 50K for 10 grams or 5K per gram. Fine. So if I go and tell that guy that I want 3.14159 or pi grams of gold, this is pi. So if I want 3.14159265397, these many grams of gold, he'll possibly call the hospital and get me admitted to a mental ward. So what would I do? Instead I say that, okay, to make life simple for both of us, I want 3.14 grams of gold, or if I'm too finicky, I would say 3.142 grams of gold. Right? This is what we do. We round off. We generally, for simplicity, we we round things off, we round numbers off, and make our and life simple in general. Now the fun thing is that this pi with infinite precision is an irrational number and cannot be stored in binary notation into finite number of right. Cannot store pi as I cannot store pi in a flip flop,
Yes, sir.
right? But I can always store 3.142 in, so I can always store 3.142 in a finite number of flip flops using whatever. So you have done encoding decimal numbers.
Yes, sir.
So there's the IEEE format for encoding decimal numbers. There are a lot of formats. So using any of those formats, we can say this is I'm using the one that you guys might have used for in your digital electronics course. I can say that this is 11 dot 0 0.1251 and something like this. But when but you can get this with a finite precision. 0.625 is 0, 0.3125 is 0, 0.15625, yeah, 0.15625 would be needed 1, and then possibly zeros. So I can represent this 3.142 in finite decimals like this, or in fractions of 2 like this, and that I can store in a register, but I cannot store pi. So basically quantization is what we studied in lower classes as rounding off. This was in class 4th or class 5th. The quantization is a fancy name for that. So basically what we say here is that, so what we do in rounding off, say in rounding off, say to 3 decimal places or 2 decimal places, if the number lies between x dot yz -1 5 to x dot yz 4, then we approximate it as x dot yz, right? This is the general rule
Yes, sir. Yes, sir.
for
Yes, sir.
quantization. Actually, this shouldn't be 4. This should be 5 minus, because 4999999 would also be approximated as x dot yz, right?
Yes, sir.
So in general, for quantizing the real line or quantizing xn in real line, we partition R into n levels or n sets. So here the only constraint is that instead of mapping to the nearest decimal number, you are mapping it to some fixed number. We partition R into n sets, A1 to AN, AI equals -1 to AI semi-closed interval, and A0 equals minus infinity, AN equals infinity. Fine. This is a partition of the real line.
Yes, sir.
Yes. So you can say that fine. Now the quantization rule is if xn equal to
So these sets need not be equal, right?
no no
In the length sense. Okay.
no. So these won't definitely won't be equal because see a1 will always be minus infinity to a0 and an will always be right.
Yes, sir. Minus infinity to a1, sir, I think.
Sorry, a1. Sorry. Yeah. This will be so these need not be equal in length. We'll consider a special case of uniform quantization where these are equal, but generally these need not be equal. So that we'll cover in detail in the next semester. But right now, also since these are partitions, AI intersection AJ is the empty set. Fine. And xn is this, q of xn is bi. These two are taken care of. And so the first thing that you would notice about this, that unlike sampling, where we can reconstruct the true signal from its samples, quantization is a lossy process. Once I tell you something is 3.14, you cannot say that it's pi, right? I tell you it is 3.14, 3.142, you cannot say that it's pi. 3.142 is an approximation. Or I tell you there were approximately 10,000 grains of sand in something. As soon as I say there was approximately 10,000 grains of sand, you cannot say that whether there were 10,100 or 9,999, something like that. You just give an approximation. Even about JEE ranks. So when your JEE rank is within the top 10, you say it with exact precision, or even in the top 100. And once it goes into the thousands, you reduce the precision to say within 100. So everything above 1050 becomes 1100 and like that. And once you cross 10,000 like me, then everything above 10,000 between 11,000 becomes 10,000 and so on, right? But once you tell someone that your JE rank was around 10,000 or your JE rank was around 1,000, they cannot go back and tell you that it was 983 or 1,048, something like that, right? Hmm?
Yes, sir.
Yeah, excellent. So sampling quantization is a lossy process. So since this is a lossy process, is a process. We are actually losing precision when quantize. Fine. We are losing precision when we quantize. And this we define as the quantization error x tilde of n equals xn minus right. This is right. Any problems? I don't think you have any problems with this definition.
Yes, sir.
Excellent. So error, you have done this in class 11th in physics, the first chapter. Did you guys do the first chapter of physics? That
Yes, sir, for
dimension
means.
analysis and stuff like that. So there we have one nice property of error, that error is always zero mean. If it is not a zero mean error, then it means that there is some problem with your measurement process that you need to take care of manually, right? So the average error is always zero, unless it otherwise it's not error, it's some uh, fallacy that you have introduced into the system. Agreed?
Yes.
So instead, instead of trying to, so if we say that we are losing information, and since we are losing information, or we are losing some precision, we would want to minimize that loss in the precision, because we want to get the signal across with as much precision as possible. So we would want to minimize, so, and we want to minimize the error. Fine. And since the error is zero mean, we try to minimize the error power, or the mean squared error. Expectation of this. We try to minimize the error in the average sense. Fine. So Adit, this answers your old question.
Okay, sir.
Okay. So there for sampling a random process, you prove that the mean squared error is zero. This.
So, is this related to somehow our ability to reconstruct the signal
Yes.
after that?
Yes. Yes.
Okay.
So the larger this error, the harder you will find it to reconstruct the signal. Okay. So I think I'll elaborate on minimizing this in the next class, because you have a quiz as well. So we'll stop here for today. Okay. Bye. Have a nice day. All the best for the quiz.